Upsetting developments? Well, maybe I should have named this video Developing Upsets, because today we are not taking a look at the emotional state of contemporary blacksmithing. We are instead taking a look at the blacksmithing technique of upsetting. Quite frequently in the videos we are drawing out, and drawing out is taking a bar and making it longer and thinner, such as making this pair of tong reins out of a piece of 3/4 inch square bar. And that is a very common technique. Now the exact opposite is true of upsetting. That is taking a bar and making it shorter and thicker. And in today's video, I'm not really looking at specific techniques for upsetting, nor am I looking at a specific project. But instead today I would like to look at what happens when you use different tools for creating the force that causes the upsetting. Now there is a scientific formula that explores force as it would compare to the weight of the hammer versus the speed at which you swing a hammer. And while that applies to what we're doing today, I don't know that formula off the top of my head, and we aren't really going to look at the math of that formula and try and test that formula out. Instead, I just want to see how the material behaves differently, or if it behaves differently, comparing a 2-pound hammer to do the job versus a 4-pound hammer to do the job, versus using the power hammer, and finally taking a look at what the hydraulic press might do. And this won't be about which tool gets results the fastest. We will certainly see how that plays out, and we can probably make some pretty good guesses on which one of these is going to be faster and which one is going to be slower to create the upset. But what I'm really looking at is, what does it do to the material? Is the nature of the finished upset different under all of these different tools? And to do that, I'm going to start with 4 pieces of 1-inch square bar, 3 inches long. Now somebody's going to want this in millimeters. It doesn't matter. These are just standard sizes that I can use for repeatable results, so I can compare them all and see what I did. You can use 1.5-inch bar, you could use 3/4 inch bar. It really doesn't matter, but that's 25 millimeter square bar, 75 millimeters long. Again, the size of the bar is not the point. The only reason I need to know what I'm starting with is because I want to take them all to the same point. I want to reduce every bar by 1 inch, so I'm going to upset them the long way till it is a 2-inch tall bar, and whatever dimension it ends up, however it looks when it's done, that's what I want to find out. Is it going to flare out at the top? Is it going to bulge out in the middle? Is it going to be perfectly even, but a bigger cross section of square? That's the point of today's little experiment. So let's go put these in the forge and let's get started. I'm going to start with the 2-pound hammer. That's the one that seems like it'll probably be the most difficult and take the longest to accomplish. And every time I come out of the fire, I'm going to stand the same end up. And that's just to get a relative indication on how much work the hammer is doing and how much work the rebound of the anvil is doing. I may have to find a better pair of tongs too. Let's see if these tongs hold better. Much better. Again, I just want to go to 2 inches. That's at 2.5, so I can go a little bit further. And I want to keep it hot. I don't want cooling off to have a big factor in this. And certainly swing a 2-pound hammer a lot faster than I can swing the 4-pound hammer, I suspect. That's almost there. I have to start working around the edges so I don't just create a hollow in the middle. That went a little faster than I thought it might. That's at 2 inches now. So that's what our 2-pound hammer did for us. We'll take some measurements after we're all done. So now we'll go to a bigger hand hammer and see if the results are any different. I'm sure I'll swing this much slower. This is actually a 2,000 gram hammer. So that's 2 kilograms, so it's really 4.4 pounds. But even though I'm swinging this much slower, we're getting down to size pretty quickly. Heat it up one more time and finish it. And again, I'm leaving the same side up for both heats. Okay, that one's at 2 inches. Very similar effect, but it did go much faster with a bigger hammer, which presumably just means that I can't swing this lighter hammer fast enough to get the effect just as fast. Next we'll go under the 60 kilogram air hammer and we'll be working just on the flat section of the dies. Much faster and more efficient, just like we thought it might be, but it also results in a little bit different shape because it's upsetting in a different place. Now I have no idea how much faster or slower the blows from the power hammer are. I have never counted how many blows per minute I strike with any given weight hammer, and of course that changes throughout the day, so I'm not sure if that's really relevant. And again, it isn't exactly the point of the test today. For our final section of bar, let's go to the hydraulic press. Now once again, you can see that this is a little bit different shape, but also very quick and effective way to upset a short bar like this. Well, what, if anything, have we learned? Well, for one thing, my initial suspicion is confirmed. The way you apply force to the material affects the way the material comes out. It isn't just hit it more times with a lighter hammer and get the exact same result you do with a power hammer. Now, certainly if you're working on a project, you can work that way. With these that are flaring out widely at the top and are much more upset at the very top surface where the hammer impact was, if you work that back down and then upset it some more, you can move that upset down into the bar. But that wasn't the point of this experiment. I just wanted to see how the bars behaved under different hammers and with different machinery. So the first bar that we did just with a 2-pound hammer at the anvil, and it took several heats to do this. It's 2 inches long, which was what our goal is, and the top is about 1.5 inches square. The bottom is 1.25 inches square. So there is some effect from the anvil, and that's what. And when we talk about anvil rebound, that's what we're talking about. The force from the hammer travels through the material you're working on down into the anvil, where it is either lost because your anvil has no rebound, or it is reflected back up into the work because of the anvil's rebound, and that's why this starts to thicken out. Not just at the top, but also at the bottom. In the middle, it's about 1 1/8 inches. So the vast majority of the upsetting occurred at the top. There's a little bit more on the base where it was at the anvil, and very little occurred in the middle of the bar. Now, if we look at the bar done with the 4-pound hammer, we find that it is just under 1.5 inches at the top. So about 1 3/8 inches. The force from that hammer blow had to go somewhere else if it didn't upset the top. Did it upset the bottom? Well, this is also 1.25 inches. So that force wasn't really transferred down to the anvil and then reflected back up through rebound any more than it was with a 2-pound hammer. But it's a little bit more than 1.125 inches in the middle. So more of that force from the heavy hammer went down to the middle. You can also look at these side by side, and the top upset transitions more gradually as it goes from the top surface down in. This one, most of it's confined right at the top, and this one has a longer taper down to the part that's still at 1.125 inches. So that's another thing. The heavier hammer transfers more work into the center of the bar. The lighter hammer, the work mostly occurs at the surface of the bar. We can look at that in a little more detail with the one done under the power hammer. This one, the top surface is 1.125 inches, which is what the middle surfaces were on these others. It's still 2 inches long. The center is about 1.25 inches. Very interesting. And the bottom is 1.125 inches. Because of the extra force of the power hammer, most of the energy went to the center of the bar, and only some stayed at the ends, and there's no flaring at the ends. Now the bar is starting to get off center. This is something you have to work to correct constantly with upsets. And don't let it get real twisty and bendy, because it's really hard to correct at that point. But for the sake of this experiment, this is exactly what I was looking to compare and see what happens under these situations. Now our final bar we did under the hydraulic press. Again, it's right at 2 inches. The top of the bar is 1.16 inches. It hardly upset at all at the top. Same at the bottom. All of that energy went right into the middle. This got considerably bigger in the middle. 1.25 inches on one side, or 1 3/8 on the other side. So a lot more of the force went right to the middle. That's a 24-ton squeeze, so that's a lot of pressure. Instead of having some of the energy absorbed right at the top and some of the energy reflected from the bottom, in the press it all transfers to the middle, so you get that really nice upset right in the center, and that can be an important concept. Similar effect with the power hammer, just not quite as dramatic. Now what has all that got to do with the price of hammers in Australia? Absolutely nothing. It's just a look at how essentially the same technique but using different tools can affect your material. And this is how you can learn things in blacksmithing. Don't just theorize, don't just read, don't just watch YouTube videos, even though I really appreciate you watching the YouTube videos. Get out to your shop, do some experimenting. If right now you're thinking, what would happen if? Well, don't ask me, because I just did these 4. Get out to your shop, try that if, and then put it in the comments. Well, I tried it doing it this way, and this is the result I got. Did you do it with an 8-ounce ball peen hammer? Did you do it with drawing out dies? Do you have an upsetting machine? They actually make machines just for doing specialized upsets. And of course, the way you heat material changes the way you upset. This isn't a project-based experiment. This is just a look at how the same technique can be affected based on the tools you choose to use. So go do some experiments with the tools you have in your shop and see how that works out. You don't have to do it with 1-inch square bar, do it with 3/4-inch square bar, do it with something heavier. Don't do it with anything too skinny, or it'll just fold in half, and that won't be a very good test. I thought this was a fun experiment. I hope you enjoyed it. If you did, give it a thumbs up. If you haven't done so already, I would love it if you hit that subscribe button. Feel free to stick around, watch a few of the other videos, share the videos with your friends if you'd like. But then by all means, get out to your shop, try out some new techniques, or use different tools for techniques that you already know how to use. But do challenge yourself, and of course, stay safe, wear your safety glasses. We'll see you for the next one.